And now in this lecture I'll answer two questions. The first question, we find out the radius of this circle. Quadrilateral ABCD is inscribed by this circle, and we have to find out the radius of this circle that blocks quadrilateral ABCD. The second question, we find out the length of this line segment AP is equals to x. We have to find out the value of x. So we start with the first question. So in the drawing we have quadrilateral ABCD that is inscribed by this circle. You know that AC is the diameter of this circle. Side AB of quadrilateral ABCD equals to side BC. Again, also know that the perimeter of this quadrilateral ABCD is equal to 18 units in total. That is to say, the sum of the four sides, the sum of the four side lengths of quadrilateral ABCD is equal to 18. That is to say, AB plus BC plus CD plus DA in total they are equal to 18. And we also know that the area of this quadrilateral ABCD is equal to 16 square units in its side. Again, our task is to find out the radius of this circle that blocks quadrilateral ABCD. So first of all, we define the side lengths of this quadrilateral ABCD by name. We define the length of side AB as A. AB equals to A, and therefore BC must be also equal to A because they are equal to each other. We define the length of side AD as B, and finally we define the length of side CD as C. So here we can implement rule 7. Repeat quickly on rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle. This is peripheral angle ACB that subtend on chord AB, this is the diameter of the circle, and therefore it is equal to 90 degrees in its size. So according to this rule 7, any peripheral angle that subtend on the diameter of the circle must be equal to 90 degrees in its size. Peripheral angle ACB equals to 90 degrees in its size. So we can implement rule 7 in our drawing. In our drawing we have, this is peripheral angle ABC that subtend on chord AC, that is the diameter of this circle, and therefore according to rule 7, peripheral angle ABC must be equal to 90 degrees in its size. Likewise, this is peripheral angle ADC that also subtend on chord AC, that is the diameter of the circle, and therefore it must be equal to 90 degrees in its size according to the same rule 7. So in the next step, we'll implement the Pythagoras theorem on those two right triangles. On the right triangle ABC and on this right triangle ADC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle ABC, according to the Pythagoras theorem, the Pythagoras theorem in the right triangle ABC. AC squared, this is the square of the hypotenuse, equals to AB squared plus BC squared. So repeat again the right triangle ABC according to the Pythagoras theorem. AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so it is AC squared equals to AB squared. AB is A, therefore AB squared is A squared plus BC squared. BC is also A, so BC squared is A squared. So in total, we found out that AC squared equals to A squared plus A squared. This is 2A squared. This is equation 1. Equation 1 states that AC squared equals to 2A squared. In the next step, we will implement the Pythagoras theorem on this right triangle, triangle ADC. On this right triangle, triangle ADC, according to the Pythagoras theorem, here by PT is the abbreviation for Pythagoras theorem. On this right triangle ADC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, is equal to AD squared plus DC squared. And again, in this right ADC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AD squared plus DC squared. AC is the missing side, so it is AC squared equals to AD squared. AD is B, therefore AD squared is B squared. Plus CD squared. CD is C, therefore CD squared is C squared. In total, according to equation 2, we actually found out that AC squared equals to B squared plus C squared. This is according to this equation 2, while according to equation 1, we already found out that AC squared equals to 2A squared. So we have two different equations for AC squared. Therefore, we get equation 3 that says that AC squared according to equation 1 must be equal to AC squared according to equation 2. According to equation 3, AC squared according to equation 1 must be equal to AC squared according to equation 2. AC squared according to equation 1 equals to 2A squared, and it must be equal to AC squared according to equation 2. AC squared according to equation 2 is B squared plus C squared. So in total, according to equation 3, we found out that 2A squared equals to B squared plus C squared. So here we divide this equation 3 by 2, and so we get that according to equation 3, A squared equals to B squared plus C squared over 2. So it is given us the question that the perimeter of this quadrilateral ABCD is equal to 18 units. That is to say, AB plus BC plus CD plus DA equals to 18. AB is A, BC is also A, CD is C, and AD is B. So in total, A plus A is 2A, so 2A plus C plus D, in total 2A plus C plus B, in total must be equal to 18 units, according to what is given as the question. So we have 2A plus C plus B, in total must be equal to 18. Again, 2A plus C plus B equals to 18, according to what is given as the question. The perimeter of quadrilateral ABCD is equal to 18 units in this left. In addition, it is given as a question that the area of this quadrilateral ABCD is equal to 16 units in its size. It is very clear that quadrilateral ABCD consists of those two shapes. This is the first shape, this is the right triangle ABC. This is the second shape that quadrilateral ABCD consists of. This is actually the right triangle ADC. So therefore, the area of quadrilateral ABCD must be equal to the sum of the areas of the two shapes, of those two shapes that it consists of. That is to say, it must be equal to the area of the first shape, that is the area of this right triangle ABC, plus the area of this second shape, that is the area of this right triangle ADC. So the area of quadrilateral ABCD in total, it must be equal to the area of the first shape that it consists of, the area of this right triangle ABC, plus the area of this second shape that quadrilateral ABCD consists of, the area of this right triangle ADC. So here, this is question 5. The question 5 says that the area of quadrilateral ABCD in total must be equal to the sum of the areas of those two shapes that it consists of. It consists of right triangle ABC and the right triangle ADC. So the area of quadrilateral ABCD in total must be equal to the area of the first shape, that is the area of right triangle ABC, plus the area of the second shape, that is the area of triangle ADC. It is given as a question that the area of quadrilateral ABCD is equal to 16, so we substitute the area of quadrilateral ABCD by 16, and is equals to the area of triangle ABC. What is the area of this right triangle ABC? The area of this right triangle ABC equals to the base AB times the height BC over 2. AB is A, BC is A, so over 2. So in total it is A times A over 2. A times A is A squared over 2. So in total we should find out that the area of this right triangle ABC is equal to A squared over 2 square units in size. The area of the right triangle ABC equals to A squared over 2 square units in size, plus the area of this right triangle ADC. The area of this right triangle ADC equals to the base AD times the height DC over 2. AD is B, DC is C over 2. So in total it is B times C over 2. The area of the right triangle ADC equals to B times C over 2. So in total we should find out that according to equation 5, 16 equals to A squared over 2 plus B A squared over 2 plus B times C over 2. So here we multiply this equation by 2. And finally we get that 16 times 2 is 32. So 32 equals to A squared over 2 times 2 is A squared plus BC over 2. A squared over 2 times 2 is A squared plus BC over 2 times 2 is BC. So in total, according to equation 5, we actually found out that 32 equals to a square plus bc. But according to equation 3, a square equals to b square plus c square over 2. Again, according to equation 3, we already found out that a square equals to b square plus c square over 2. So we substitute a square in this equation 5 by b square plus c square over 2 from equation 3. Okay? And that is according to equation 5. (32) equals to a square according to equation 3 is b square plus c square over 2 and here plus bc. And so that we found out that 32 equals to b square plus c square over 2 plus bc. So here we multiply bc by 2 and then we divide it by 2 in order to account factor of this expression. And get in total that according to equation 5, 32 equals to b square plus c square over 2, and here bc times 2 is 2 times bc over 2. We multiply bc by 2 and then we divide it by 2. So we change nothing. It is allowable to multiply anything by 1. So in total, we found out that 32 equals to b square plus c square plus 2 times b times c over 2. Actually, we have the algebraic identity that says that a square plus b square plus 2 times a times b equals to a plus b square. So according to this algebraic identity, we get that b square plus c square plus 2 times bc will be equal to b plus c square divided by 2 equals to 32. So according to equation 5, in total we found out that 32 equals to b plus c square over 2. So here we multiply this equation 5 by 2, and finally we get that according to equation 5, (32 times 2 is 64) equals to b plus c square. 64 equals to b plus c square. So here we take a root out of this equation, and finally we get that the square root of 64 is 8 equals to b plus c. In total, we found out that b plus c equals to 8 according to equation 5. But according to equation 2, we only found out that according to equation 4, we found out that 2a plus c plus b equals to 18. According to equation 4, we only found out that a plus b plus c equals to 18. So actually you can substitute b plus c in this equation 5 in this equation 4 by 8 on this equation 5 because this equals to 8. So we'll do it now. We're going to according to equation 4 2a and b plus c according to equation 5 is 8 equals to 18. So in total according to equation 4 we actually found out that 2a plus 8 equals to 18. Here we subtract 8 from this equation. And finally get that according to equation 4 2a equals to 18, 18 minus 8 is 10. 2a equals to 10. Here we divide this equation 4 by 2 and finally get that a according to equation 4 a equals to 10 over 2 to this 5. So according to equation 2, we actually found out that a equals to 5 units in its length. So BC equals to A and A equals to 5. Likewise, AB also equals to A and A equals to 5. So the next step, we're going to implement the Pythagoras theorem on this triangle ABC. So I derive this triangle ABC according to the Pythagoras theorem. AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. Again, in this triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC square is the missing side, so here it is, so it is AC square equals to AB square. AB is 5, therefore AB square is 5 squared, that is 25, plus BC square. BC is also 5, so BC square is 5 squared, that is 25. So in total we actually found out that AC square equals to 25 plus 25, that is 50. AC square equals to 50. Here we substitute 50 by 25 times 2, so AC squared equals to 25 times 2. Here we take a root out of this equation and finally get that AC, the diameter AC, that also the hypotenuse of the other ABC, is equals to the square root of 25, that is 5, so inside root we left only with 2. So the diameter of this circle AC is equal to 5 times root of 2 units in its length. Our task is to find out the radius of this circle. We define the radius as R. So the radius R must be equal to the diameter over 2. This is to say it must be equal to AC over 2. AC is 5 times root of 2, and we have to divide it by 2 in order to get the radius. So we found out that the radius R equals to 5 times root of 2 over 2 units in its length in terms of numbers is equal to 3.536 units in its length. And again, I should find out that the answer to the question is that the radius of this circle r equals to either 5 times square root of 2 over 2 units in its length, or in terms of numbers, the radius r of this circle is equal to 3.536 units in its length. So I finish with the first question. In the next step, I will present to you the second question and answer the second question of this lecture. Our task on the second question is to find out the length of this line segment AP is equals to x. We have to find out the value of x. So in the moment, this is the right triangle ABC that blocks this circle, or in other words, this circle is inscribed by the right triangle ABC. In addition, this is a tangent SC that is tangent to this circle at this point, so we define the point of tendency of tangent SC with this circle. This point is point M. In addition, it is given us the question that this is line segment SQ that equals to 25 units in its length. Likewise, this is called QP is equals to 24 units in its length. Again, our test is to find out the length of this line segment AP is equals to x. We have to find out the value of x. So first of all, we will implement rule 2 in our drawing. So I repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing, we have a circle. This is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. The length of tangent PA is equal to the length of tangent PB, or PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Well, if we focus on this common external point, point A, from this common external point, point A, we have two tangents to this circle, tangent AP and tangent AQ. And according to rule 2, they are equal to each other. That is to say, AP equals to AQ. But AP equals to x, therefore AQ must be also equal to x units in its length. Likewise, we define the length of tangent BM as A. So from the common external point, point B, from this common external point, point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ, but BM is A, therefore BQ must be also equal to A units in its length. In the next step, we'll focus on this point, point S. From this point, point S, we have tangent SM. to the circle, the descendant of the circle is point M. Likewise, we have here chord QP of the circle, the extended chord PQ, such as point S. So here actually all the requirements for full 10 are satisfied, and therefore we can implement rule 10 in our drawing. Okay, click on rule 10. According to rule 10, rule 10 is true in any circle. So in any circle, if AB is any chord in the circle and PT is a tangent to the circle, then the following equation is true. That PT square equals to PA times PB. Again, PT square equals to PA times PB. So in the drawing, we have a circle. From this convex point P, we have tangent PT, that is tangent to this circle is point T. Likewise, this is chord BA, and the extended chord BA touches chord P. Yeah, the extended chord BA touches point P. So in this drawing, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So as I mentioned before, all the requirements for full 10 are satisfied. If we focus on the convex point S, we have tangent SM, that is tangent to this circle, and point M. Likewise, the extended chord PQ touches point S. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10 in our drawing. According to rule 10, SM square equals to SQ times SP. Again, SM square equals to SQ times SP. So I write it down. SM square equals to SQ times SP. Again, if you focus on the convex point S, the following equation is true according to rule 10. SM square equals to SQ times SP. SM is the missing tangent, so there it is. So it is SM square equals to SQ. SQ is 25 times SP. SP in total equals to SQ, that is 25, plus SP, that is 24. So in total, SQ equals to 25 plus 24, that is 49. So SP in total equals to 49. So she found out that SM square equals to 25 times 49. So here we'll take a root out of this equation, and finding that SM equals to the square root of 25, that is 5, times the square root of 49, that is 7. So in total, SM equals to 5 times 7, that is 35. So tangent SM equals to 35 units in its length. SM equals to 35 units in its length. This is tangent SM, that equals to 35 units in its length. What is the length of this line segment? SB. SB in total equals to SM plus BM. Again, SM plus BM equals to SB. So write it down. the missing 97 SB is equal to SM minus BM. So SB in total equals to SM, that is 35, minus BM, that is A according to our definition. So in total, SB equals to 35 minus units in its length. This is 97 SB, that equals to 35 minus units in its length. In the next step, we'll implement the Pythagoras theorem on this right green triangle SQB. And again, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle SQB, according to the Pythagoras theorem, we get that QS squared, that is the square of the hypotenuse, equals to QB squared plus SB squared. Okay, again, in the right hand triangle SQB, according to the Pythagoras theorem, QS squared equals to QB squared plus SB squared. The hypotenuse QS equals to 25 units in its length, therefore QS squared is 25 squared, that is 625. And it is equals to QB squared. QB is 8, therefore QB squared is A squared plus SB squared. SB is 35 minus 8, therefore SB squared is 35 minus A squared. So we have found out that 625 equals to A squared plus 35 minus A squared. So here we'll open the brackets of this expression and get that 625 equals to A squared plus 35 minus A squared equals to 35 squared, that is 1225 plus A squared, minus 2 times 35 times A is minus 70A. So here we'll subtract 625 from this equation. So here we'll have to nothing, 0 equals to A squared plus A squared is 2A squared. And also here, minus 78. 1225 minus 625 is 600. So in total, we should find out that 0 equals to 2A squared minus 78 plus 600. Here we will divide this equation by 2, and when we get that 2A squared over 2 is A squared, minus 78 over 2 is minus 45A, and 600 over 2 is 300, 0 over 2 is 0. So in total, we should find out that A squared minus 45A plus 300 equals to 0. And again, in total, we found out that A squared plus 45A plus 300 equals to 0. So actually, This is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, a squared minus 35a plus 300, the variable that we are looking for is a, so x equals to a. The coefficient a equals to 1. The coefficient b equals to minus 35. And finally, the coefficient c equals to 300. So we have all the data for our specific quadratic equation. So the only thing that we have to do is to put the data inside this general formula for x, and this way we get the value of a, because x equals to a. A is the variable that we are looking for. So we do it now, and we get that x equals to a, so let's substitute x here by a is equals to minus b. b is minus 35, therefore minus b is minus 35, that is 30 plus 35. And we have here plus minus the square root of b squared. b is minus 35, therefore b squared is minus 35 squared, that is 1225. And we have here minus 4 times a times c. So it is minus 4 times a is 1, so it is minus 4 times a, that is minus 4 times c. C is 300, so minus 4 times 300 is minus 1200. Divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, we have found out that a equals to 35 plus minus. Inside the root we have 1225 minus 1200, that is 25 over 2. So in total, we found out that a equals to 35 plus minus, the square root of 35 is 5 over 2. So a equals to 35 plus minus 5 over 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 35 plus 5 over 2. 35 plus 5 is 40, and 40 over 2 is 20. So the first solution for a is that a equals to 20 units in its length. And the second solution for a is that a equals to 35 minus 5 over 2. 35 minus 5 is 30, and 30 over 2 is 15. So the second solution for a is a equals to 15. Okay, we have two solutions for a. And in the next step, we will do a construction, that is to say, actually, before that we have, this is triangle AQP. Triangle AQP is an associated triangle. Why triangle AQP is an associated triangle? Because side AQ equals to side AP. The base of the associated triangle AQP is QP. So from the vertex A of triangle AQP will go perpendicular on the base QP. Again, from the vertex A of the associated triangle AQP will go perpendicular on the base QP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We find the touching point of the perpendicular from point A in QP. This point is point Z. So we have the associated triangle AQP. We go perpendicular AZ to the base QP. Yeah. And the associated triangle AQP, we go perpendicular AZ to the base QP. So here we can implement rule 21. Repeat quickly on rule 21. According to rule 21, the perpendicular to the base of an associated triangle bisect the base. So in the drawing, you have the associated triangle, triangle ABC. Triangle ABC is an associated triangle because side AB equals to side AC. For the vertex A, we go perpendicular AO to the base BC. Again, from the vertex A, we go perpendicular AO to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. The perpendicular AO is not only perpendicular to the base, but AO also bisects the base according to this rule, rule 21. Again, AO is also perpendicular AO also bisects the base BC. This is to say, divide the base BC into two halves. The first half BO equals to BC over 2, the second half OC is also equals to BC over 2. So BO equals to OC equals to BC over 2. So the perpendicular to the base of an associated triangle bisects the base. So we can actually implement rule 21 in our drawing. What put in our drawing? We have the perpendicular AZ to the base QP, and according to rule 21, that the perpendicular AZ bisects the base QP. So the first half is QZ, the second half is ZP. And again, according to rule 21, perpendicular AZ bisects the base QP. So, of course, QZ equals to ZP. The first half QZ, of course, equals to the second half ZP. And each half equals to QP over 2. Again, the first half of QP is QZ, and it equals to the second half of QP, this is ZP, and each half, of course, equals to QP over 2. QP is 24. Therefore, QP over 2 is 24 over 2. 24 over 2 is 12. So do that. From this equation, we graph that QZ equals to ZP equals to 12. QZ equals to ZP equals to 12. QZ equals to 12 units in its length, and ZP also equals to 12 units in its length, according to Rule 21. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if the size of this vertex angle is alpha, then the size of this vertex angle must also equal to alpha, because they are equal to each other according to the rule that I mentioned. So in this right triangle AQZ, alpha plus 90 degrees plus the missing angle must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees. That is the sum of the angles in any triangle. CM is a tangent. SM is tangent to the circle at point M. SM is a tangent, the absolute is straight line. So if you focus on the upper side of the straight line SM at point B, here the sum of the angles must be equal to 180 degrees according to Rule 3. Rule 3 states that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line SM at point B? We have this angle, this is the right angle, plus this missing angle. Total the sum of those two angles must be equal to 180 degrees according to Rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. And therefore, the green triangle QBS is the right triangle. So in the right triangle, we write green triangle QBS. This angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. It's very easy to see from the drawing that those two right triangles are similar to each other according to angle similarity rule. That is to say that this triangle the right triangle AQZ is similar to this triangle AQSB, to this triangle QSB according to angle similarity rule. That is to say those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So we should find out that all the figures of this green triangle, green right triangle SQB are corresponding equal to all the figures of this green right triangle AQZ, and therefore those two right triangles can point to each other according to angle similarity rule. So I write it down. And we found out that the right green triangle QBS is similar, this is the sum of similar to the right green triangle AQZ according to angle similarity rule. And again, I should find out that the right triangle QBS is similar to the right triangle AQZ according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side QS of this right triangle SQB or side AQ of this green right triangle AQB is equals to side QB of this right triangle SBQ over side QZ of this right triangle AQZ. So SQ over AQ equals to QB over QZ. Again, from the fact that those two right triangles are similar to each other, we know that the following relationship exists between their sides. We derive that side SQ of the right triangle SQB or side AQ of the right triangle AQZ is equals to side QB of the right triangle SPQ or side ZQ of the right triangle AQZ. SQ equals to 25 units in its length over AQ. AQ equals to X and X is the variable that we are looking for in this question. And it is equals to QB. QB equals to A according to our definition. Or QZ. QZ equals to 12 units in its length. So in total, we actually found out that 25 over X equals to A over 12. So here we cross multiply this equation. And finally we get that 25 times 12 equals to 8 times X. 25 times 12 is 300, so 300 equals to 8 times X. Here we divide this equation by A and finally found out that X equals to 300 over A. So actually found out that A could be equal to either 15 or 20. In order to find out which is the right value for A, I will know which is the correct value for A. I draw this ABC in a page with its circle. With its value on it. Analyze this triangle with the circle in order to find out what is the real value of A. A equals to either 15 or 20. And find out what is the real value for A. What is the correct value for A. Okay, this is the outline ABC that according to the original drawing. This circle is described by the big outline ABC. So, first of all, we define the center of this circle. This point is point O. Repeat again that point M is the point of tendency of BC with this circle. So we join points O and M together by a straight line. Point O is the center of this circle, point M is the point of the circle itself, therefore OM is the radius of this circle that we define as R. The radius OM that equals to R, the radius OM is 1 to point M, that is the point of tendency of tangent BC with this circle. And again, the radius OM is known to point M, that is the point of tendency of tangent BC with this circle. And whenever your radius that is on to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Point Q is the point of tendency of tangent AB with this circle. So we join points O and Q together by straight line. OQ is of course the radius of this circle, it equals to R. And according to rule 1, this angle equals to 90 degrees, and this angle equals to 90 degrees. I will not repeat on the same explanation, it is exactly the same explanation, for the reason that this angle equals to 90 degrees. Okay, so in quadrilateral QOMB we have 1, 2, 3 angles, and therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral, the small quadrilateral QOMB we have 4 angles, and therefore we can relate to quadrilateral QOMB as a rectangle, although this is actually a square. Relate to quadrilateral QOMB as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle QOMB, side OM equals to the opposite side QB, but OM is out, therefore the opposite side QB must be also equal to R units in its length. So QB equals to A equals to R. Okay. Or we can write down that A equals to R, or A equals to QB equals to R. A equals to QB, and QB of course equals to R. In the next step we will do a construction, that is to say we will extend the radius MO by a straight line until it touches the circle. When you find the touching point of the extended radius MO with this circle, this point is point T. MO is the radius, it is absolutely a straight line. When you extend a straight line by straight line, the result MT must be also a straight line. So MT is a straight line. MT is a straight line, so if you focus on the right side of the straight line MT is point O, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the right side of MT is point O? We have this angle that is the right angle, plus this missing angle, in total must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. Actually MT is a chord because it touches the circle at 2 points M and T, therefore it is a chord that passes through the center of the circle, and therefore MT is the diameter of the circle, point O is the center of the circle, point T is the point of the circle itself, therefore OP is the radius of the circle that is equals to R. In the next step we will do another construction, that is to say we will go tangent to the circle that will be tangent at point T. We do a tangent to the circle that will be tangent to the circle at point T. from AB. When you find the touching point of the tangent with side AB, this point is point S. So ST is a tangent to the circle at point T. The radius OT is equals to R. The radius OT is drawn to point T. That is the point of tendency of tangent ST with this circle. And whenever your radius is drawn to the point of tendency, then tangent ST will be perpendicular to the radius TO. If ST is perpendicular to TO, it means that this angle equals to 90 degrees according to rule 1. So actually, in the small quadrilateral, the small upper quadrilateral TOQS, we have 1, 2, 3 rectangles, and therefore this fourth missing must be equal to 90 degrees in its sides. So in quadrilateral STQO, we have 4 rectangles, and therefore we can write for quadrilateral QOST is a rectangle, although that it is also it's actually a square. So write for quadrilateral STQO is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the upper quadrilateral STOQ, TO side QO must be equal to the opposite side SQ, but TO is R, therefore the opposite side SQ must be also equal to R units in its length. What is the length of AQ? AQ equals to X, and AQ also equals to AS plus SQ. Again, AQ equals to AS plus SQ. So can I know that AQ equals to AS plus SQ? But SQ is also AQ in total equals to AS plus R. Again, AQ equals to AS plus R. AQ equals to AS plus R. And AQ also, of course, equals to X. And can I do AQ equals to X? AS plus R is definitely greater than R, because AS is a positive number. Again, AS plus R is definitely greater than R. So you can write here that AS is greater than R. AS plus R is greater than R. And from this long inequality, we derive that X is greater than A, and X is greater than A. Okay? X is greater than A. Found out that A can get two values, can be equal to either to 20 or to 15. First of all, we found out that X must be greater than A. A could be equal to either 20. By solving the quadratic equation, we add two solutions for A. A either equals to 20, or it also could be equal to 15. Okay, we have two solutions for A. Well, we found out that x equals to 300 over a. So we found out that x equals to 300 over a. So if a equals to 15, then x equals to 300 over 15, this is 20. So if a equals to 15, then x equals to 20. Likewise, here, if a equals to 20, then x equals to 300 over 20, this is 15. Repeat again. If a equals to 20, x equals to 15, and if a equals to 15, if a equals to 15, then x equals to 20. So here we have x that is equals to 15 is less than 20, because 15 is less than 20, and 20 equals to a. So from this inequality, we derive that x is smaller than a. X is less than a. Okay, x is less than a. X is less than a. Well, we only found out that x must be greater than a, so there is a contradiction. X is greater than a, therefore x must not be less than a. So due to this contradiction, we present the solution, the incorrect solution, and we're left only with the other solution that is possible for a. If a equals to 15, then x equals to 20. So x equals to 20, and 20 is definitely greater than 15, is equals to 8. So from this inequality, we derive that x is greater than a. X is greater than a, exactly like the I already found out that x must be greater than a. It is not contradicts our previous findings that x must be greater than a, and therefore the solution to the question is that x AP is equals to x equals to 20 units in its length. Again. So if we found out that AP is equals to x is equal to 20 units in its length. And that is the answer to the question. So in the next step, I'll summarize the lecture. We start with the first question, of course. Repeat on the first solution of the first question. Our task in the first question is to find out the radius of this circle. So actually we have here quadrilateral ABCD is inscribed by this circle. That is to say, this circle blocks quadrilateral ABCD, and our task is to find out the radius of this circle that blocks quadrilateral ABCD. We know that AC is the diameter of this circle. We know that side AB of quadrilateral ABCD equals to side BC. And we also know that the perimeter of this quadrilateral ABCD is equal to 18 units. That is to say, the sum of its sides lengths, the sum of its 4 side lengths, in total it is 18 units. That is to say, AB plus BC plus CD plus DA equals to 18. In addition, we know that the area of this quadrilateral ABCD is equal to 16 square units in size. So our task is to find out the radius of this circle that blocks quadrilateral ABCD. So first of all, we define the length of side AB as A. AB equals to BC, therefore BC must be also equal to A. We define the length of side AD as B. We define the length of side CD as C. So here we can implement rule 7. Repeat quickly on rule 7. According to rule 7, a peripheral angle that subtends on the diameter of the circle, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing, we have a circle. This is peripheral angle ACB that subtends on the diameter of the circle. For AB is the diameter of the circle. And therefore, peripheral angle ACB equals to 90 degrees in its size. So according to this rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. A peripheral angle ACB equals to 90 degrees in its size. So I can actually implement rule 7 in our drawing. We have in our drawing, this is peripheral angle ACB that subtends or called AC, that is the diameter of the circle, and therefore it must be equal to 90 degrees in its size. Likewise, this is peripheral angle CDA that also subtends or called AC, that is the diameter of the circle, and therefore according to rule 7 is equal to 90 degrees in its size. So in the next step, we implemented the Pythagoras theorem on those two right angles. This is the right angle ABC, this is the right angle CDA. So first of all, implemented the Pythagoras theorem on this right angle ABC. According to the Pythagoras theorem, in a right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right angle ABC, it means that AC squared, that is the square of the hypotenuse, must be equal to AB squared plus BC squared. Repeat again, according to the Pythagoras theorem, in the right angle ABC, AC squared, that is the square of the hypotenuse, must be equal to AB squared plus BC squared. AC is the missing side, so it is equals to AB squared. AB is A, therefore AB squared is A squared plus BC squared. BC is also A, so BC squared is A squared. So in total, AC squared equals to A squared plus A squared. And AC squared equals to A squared plus A squared, that is 2A squared. So AC squared equals to 2A squared. So according to equation 1, we actually found out that AC squared equals to 2A squared. Next step, implemented the Pythagoras theorem on this right triangle ADC. This right triangle ADC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, must be equal to CD squared plus DA squared. Okay, again, according to the Pythagoras theorem, in the right triangle ADC, AC squared, that is the square of the hypotenuse, must be equal to AD squared plus DC squared. AC is the missing side, so it is AC squared equals to AD squared. AD is B, therefore AD squared is B squared, plus DC squared. BC is C, therefore BC squared is C squared. So in total, AC squared, that is the square of the hypotenuse, equals to B squared plus C squared. According to equation 2, we found out that AC squared equals to B squared plus C squared. So We have two equations for the value of AC squared. AC squared equals to 2A squared, and this is according to equation 1, while according to equation 2, AC squared equals to B squared plus C squared. Therefore, we created equation 3 that says that AC squared according to equation 1 must be equal to AC squared according to equation 2. Again, equation 3 says that AC squared according to equation 1 must be equal to AC squared according to equation 2. AC squared according to equation 1 equals to 2A squared, and it must be equal to AC squared according to equation 2. That AC squared according to equation 2 equals to B squared plus C squared. So in total, according to equation 3, we actually found out that 2A squared equals to B squared plus C squared. So here we divided the equation 3 by 2, and finally found out that 2A squared over 2 is A squared, and it equals to B squared plus C squared over 2. So in total, according to equation 3, we found out that A squared equals to B squared plus C squared over 2. We know that the perimeter of this quadrangle ABCD is equal to 18. That is to say, AB plus BC plus CD plus DA equals to 18. AB is A, BC is A, CD is C, and DA is B. So A plus A is 2A plus C plus B equals to 18. So 2A plus C plus B equals to 18. What is the equation? 4 2A plus C plus B equals to 18. The perimeter for the other ABCD. It is given as the equation that the area of this quadrangle ABCD is equal to 16 square units in its size. Quadrangle ABCD consists of those two rectangles, and therefore the area of quadrangle ABCD must be equal to the sum of the areas of those two shapes that it consists of. That is to say, the area of quadrangle ABCD must be equal to the area of the first shape that it consists of, that is actually the area of this rectangle ABC, plus the area of the second shape that it consists of, that is actually the area of triangle ABC, plus the area of triangle ADC. So, therefore, the other ABCD must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of the first shape, that is actually the area of triangle ABC, plus the area of the second shape that it consists of, that is actually the area of triangle ADC. The area of triangle ABC is 16, so we substitute the area of triangle ABC by 16 equals to the area of the triangle ABC. The area of this triangle ABC is equal to the base AB times the height BC over 2. AB is A, BC is A, so over 2. So it is A times A over 2. A times A is A square over 2. So in total, the area of the rectangle ABC equals to A square over 2 plus the area of this right triangle ADC. The area of this right triangle ADC equals to the base AD times the IDC over 2. AD is B, DC is C over 2. So in total, it must be equal to B times C over 2. The area of the rectangle ADC in total equals to B times C over 2. So in total, according to equation 5, we actually found out that 16 equals to A square over 2 plus BC square over 2. Here we multiply this equation by 2, and we found out that 16 over 2 is 32 equals to A square plus BC. And again, after we multiply the equation by 2, we found out that 32 equals to A square plus BC. But according to equation 3, we already found out that A square equals to B square plus C square over 2. Again, A square equals to B square plus C square over 2. So actually substitute A square in this equation 5 by B square plus C square over 2. And we found out that 32 equals to A square, that is B square plus C square over 2 according to equation 3, plus BC square. So in total, according to equation 5, 32 equals to B square plus C square over 2 plus BC. Here we multiplied BC by 2, and then we divided by 2 in order to have a common factor in this expression. We found out over here that 32 equals to B square plus C square over 2, and we have 2 times BC over 2. It is 2 times BC over 2. So in total, we found out that according to equation 5, 32 equals to b squared plus c squared plus 2 times bc over 2. We have the algebraic identity that states that a squared plus b squared plus 2 times b times c equals to a plus b squared. So according to this algebraic identity, we get that b squared plus c squared plus 2 times b times c equals to b plus c squared. Okay, so substitute b squared plus c squared plus 2 times bc by b plus c squared. So in total, we found out that 32 equals to b plus c squared over 2. Here we multiply this equation by 2 and we found out that 32 times 2 is 64 equals to b plus c squared. Here we took out all of this equation and we found out that b plus c equals to the square root of 64, that is 8. According to equation 5, b plus c equals to 8. And according to equation 4, we only found out that 2 times 8 plus b plus c equals to 18. Now we can substitute b plus c in this equation 5 by 8 from this equation. We can substitute b plus c from this equation 4 by 8 from this equation 5 because b plus c equals to 8. We did it and we found out that 2a plus b plus c, that is 8, equals to 18. Here we subtracted 8 from this equation and we found out that 2a equals to 18 plus 10 is 18 plus 10 is 18 plus 8 is 10. So 2a equals to 10. Here we divided this equation by 2 and we found out that a equals to 10 over 2, that is 5. Again, a equals to 5, let's see this. BC equals to A and A is 5. AB is also equals to A and A is 5. So in the next step, we created a Pythagoras on this side triangle ABC. The only missing side is the hypotenuse AC. By implementing the Pythagoras theorem in this triangle ABC, we find out the ref of the only side that is missing, that is the ref of the hypotenuse AC, that is also the diameter. And the radius that we are looking for in this question will be equal to the diameter over 2. That is to say, it will be equal to AC over 2. In this way, this will be the answer to the question. So, according to the Pythagoras theorem, in this triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. Now, triangle ABC, according to the Pythagoras theorem, AC squared equals to AB squared plus BC squared. AC squared, that is the square of the hypotenuse, equals to AB squared. Again, AB is 5, therefore B squared is 5 squared, that is 25, plus BC squared. BC is also 5, therefore BC squared is 5 squared, that is 25. So in total, AC squared equals to 25 plus 25, that is 50. So AC squared equals to 50. Here we took out all those equations. Actually, before that, we substituted 50 by 25 times 2, so in total AC squared equals to 25 times 2. Here we took out all those equations and found out that AC equals to the square of 25, that is 5 times square root of 2. So the diameter AC of this circle equals to 5 times square root of 2, therefore the radius must be equal to the diameter over 2. The radius of the circle R must be equal to the diameter AC over 2. AC is square root of is 5 times square root of 2, therefore the radius R must be equal to the diameter, that is 5 times square root of 2 over 2. So in total, the radius of the circle equals to either 5 times square root of 2 over 2, or in terms of numbers, it equals to 3.536 units in its length. And again, the radius that we are looking for this equation, the radius of this circle equals to either 5 times square root of 2 over 2 units in its length, or in terms of numbers, it equals to 3.536 units in its length. So, finished repeat on the first question. The next step, repeat on the solution of the second question. The second question, our test was to find out the value of line segment AP that equals to x. We have to find out the value of x. So in the domain, we have a circle that is described by the article ABC. Also your tangent SM, that is tangent to this circle, is point M. This is of course right angle, angle ABC is right angle. You also know that SQ equals to 25 units in its length. This is called QP. This equals to 24 units in its length. Again, our task is to find out the length of this line segment AP. This is equals to x. We have to find out the value of x. So in the next step, implement all two in our drawing. Repeat clicking on all two. According to all two, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing, we have a circle. This is the common standpoint, point P. For this common standpoint, point P, we have two tangents to the circle, tangent PA and tangent PB. According to this rule, all two are equal to each other. That is to say, the length of tangent PA equals to the length of tangent PB. Or PA equals to PB. So we can actually implement all two in our drawing. Why? Because in our drawing, this is the common standpoint, point A. From the common standpoint, point A, we have two tangents to this circle, tangent AP and tangent AQ. According to all two, they are equal to each other. That is to say, AP equals to AQ. But AP equals to x. That is the one segment that we are looking for in this question. Therefore, AQ must be also equal to x according to all two. Likewise, we define the length of this tangent BM as A. So, if we focus on this common standpoint, point B, from this common standpoint, point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to all two, they are equal to each other. That is to say, BM equals to BQ. But BM is A, therefore BQ must be also equal to M in its length. Okay, so in the next step, we focus on this common standpoint, point S. For this common standpoint, point S, we have tangent SM, that is tangent to this circle point M, and we also have here chord PQ. The extended chord PQ touches point S. So actually, all the requirements of rule 10 are satisfied, and therefore we can implement rule 10 in our drawing. So repeat quickly on rule 10. According to rule 10 is true in any circle. So in any circle, if AB is any chord in the circle and PT is a tangent to the circle, then the following equation is true. PT squared equals to PA times PB. Again, PT squared equals to PA times PB. So in the drawing, we have a circle. This is the common standpoint, point P. For the common standpoint, point P, we have tangent PT. This is tangent to the circle, point P. Likewise, this is chord BA. The extended chord BA touches point P. So in this drawing, the following equation is true. That PT squared equals to PA times PB. Again, PT squared equals to PA times PB. So we can actually implement rule 10 in our drawing. So as I mentioned before, all the requirements of rule 10 are satisfied. If you focus on this common standpoint, point S, we have tangent SM, that is tangent to the circle point M, and chord PQ, the extended chord PQ touches point S. And therefore, so again, all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, the following equation is true. That SM squared equals to SQ times SP. Again, SM squared equals to SQ times SP. So, according to rule 10, if we focus on the common standpoint point S, the following equation is true. That SM squared equals to SQ times SP. Tangent SM is the missing tangent, so it is SM squared equals to SQ. SQ is 25. times SP. SP in total equals to SQ plus QP. SQ is 25, QP is 24, so in total SP equals to 24 plus 25 plus 24, that is 49. So in total SP equals to 49. It again, SM square equals to SQ, that is 25, plus SP, that is 49. So SM square equals to 25 plus 49. So here we take out all of this equation, and we found out that SM equals to the square root of 25 is 5, times the square root of 49 is 7. So in total, SM equals to 5 times 7, that is 45. SM equals to 5 times 7, that is 35. So SM, tangent SM equals to 35 minutes in its length. Tangent SM equals to 35 minutes in its length. So what is the length of this line segment SB? SB equals to SM plus BM again. SM plus BM equals to SB. And again, SB equals to SM plus BM. So SB equals to SM, that is 35, plus BM, that is 8. So in total, SB equals to 35 plus anything is tangent SM, as a tangent, it is definitely a straight line. So if you focus on the upper side of the straight line, SB at point B, here the sum of the areas must be equal to 180 degrees according to all three. All three said that the sum of the areas on one side of the straight line is equal to 180 degrees. So which areas we have at the upper side of SM at point B? We have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. So we found out that the green triangle SQB is a right triangle. So in the next step, implement the Pythagoras theorem on this green right triangle SQB. The Pythagoras theorem, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, this green right triangle SQB, SQ squared, that is the square of the hypotenuse, equals to QB squared plus BS squared. Again, the right triangle SQB, according to the Pythagoras theorem, QS squared, that is the square of the hypotenuse, equals to QB squared plus SB squared. QS is 25, therefore QS squared is 25 squared, that is 625. And it equals to QB squared. QB is 8, therefore QB squared is 8 squared. Plus SB squared. SB is 35 minus 8, therefore SB squared is 35 minus 8 squared. So in total, we should found out that 625 equals to 8 squared plus 35 minus 8 squared. Here we open the brackets of this expression and find out that 625 equals to 8 squared plus 35 minus 8 squared. 35 minus 8 squared equals to 35 squared, that is 35 squared, that is 1225 plus 8 squared, plus 2 times 35 times 8, that is minus 78. So here a squared plus a squared is 2a squared. And we have also minus 78. And here we subtract 625 from this equation. So in this side of the equation we have nothing, that is to say 0. When on the other side of the equation we have 1225 plus 625 equals to 600. So in total we should found out that 0 equals to 2a squared plus 0 equals to 2a squared minus 78 plus 600. So here we divided this equation by 2 and we found out that 2a squared over 2 is a squared, minus 78 over 2 is minus 45a, and 600 over 2 is 300, 0 over 2 is 0. So in total we should found out that a squared minus 45a plus 300 equals to 0. So actually, a squared minus 45a plus 300, it is a quadratic equation. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, A, B, and C are the coefficient of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Now a specific quadratic equation, that is to say a squared minus 35a plus 300 equals to 0. The variable that we are looking for is of course a. So x equals to a. Coefficient a, the coefficient a equals to 1, the coefficient b equals to minus 35, and the coefficient c equals to 300. So we have all the data that is needed in order to find out the value of the missing variable a. You just have to put the data of our specific quadratic equation in this general formula for x, and this way we find out the value of the values of a, because a is the variable that we are looking for in our specific quadratic equation. So x equals to a, so substitute x by a is the variable that we are looking for, and it equals to minus b. B is minus 45, minus b is minus 45, that is plus 25, plus minus square root of b squared, square root of b squared. B is minus 45, therefore b squared is minus 45 squared, that is 1225. Minus 4 times a times c. A is 1, so minus 4 times 1 minus 4 times c. Minus 4 times c is minus 4 times 300, that is minus 1200. So total minus 4 times ac is minus 1200 divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, we found out that a equals to 35 plus minus square root of 1225 minus 1200 over 2. 1225 plus 1200 is 25 divided by 2. So a equals to 35 plus minus square root of 25 over 2. Square root of 25 is 5 over 2. So in total, we found out that a equals to 35 plus minus 5 over 2. So here we will have two solutions that are possible for a. The first solution for a is that a equals to 35 plus 5 over 2. 35 plus 5 is 40, and 40 over 2 is 20. So the first solution for a is that a equals to 20, while the second solution for a is that a equals to 35 minus 5 over 2. 35 minus 5 is 30 over 2. 30 over 2 is 15. So in total, we have two solutions for a. The first solution for a is that a equals to 20, and the second solution for a is that a equals to 15. In the next step, we did a construction, and then we implemented all 21 in our drawing, in the new construction. First of all, the right triangle AQP is an isosceles triangle. Why? Because side AQ equals to side AP. QP is the base of the isosceles right triangle AQP. So we did a construction, that is to say, from the vertex A of the isosceles triangle AQP, we draw perpendicular to the base QP. Again, from point A, we draw perpendicular to the base QP of the isosceles triangle AQP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A, the base QP. This point is point Z. So, in conclusion, actually have here associate triangle AQP, and from point A we do perpendicular AZ to the base QP. So here we can definitely implement rule 21. So repeat rule 21. According to rule 21, the perpendicular to the base of an associated triangle bisect the base. So in the drawing, we have this is the associated triangle, triangle ABC. Triangle ABC is an associated triangle because side AB equals to side AC. From point A, we do perpendicular AO to the base BC. Again, from the vertex A, we do perpendicular AO to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. According to this rule 21, the perpendicular AO bisects the base BC. Again, the perpendicular AO bisects the base BC. That is to say, divide the base BC into two halves. Each half must be also equal to BC over 2. So the first half BO is equals to BC over 2. The second half OC also equals to BC over 2. So BO equals to OC equals to BC over 2. So we can definitely implement rule 21 in our drawing. So as I mentioned before, we have here associated triangle APQ. We have the perpendicular AZ to the base QP. According to rule 21, the perpendicular AZ bisects the base QP. That is to say, each half must be equal to QP over 2. The first half QZ must be equal to QP over 2. The second half ZP must be also equal to ZP over 2 because it bisects the base QP. It means it divides it into two halves. Each half must be equal to QP over 2. So according to rule 21, the first half QZ, of course, it is definitely equal to the second half ZP, and each half must be equal to QP over 2. QP is 24 and 24 over 2 is 12. So in this equation we derive that QZ equals to ZP equals to 12. So QZ equals to 12, ZP also equals to 12 units in its length. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this vertex angles as alpha, then the size of this vertex angle must also equal to alpha because they are equal to each other according to the rule that I mentioned. So in this right triangle AZQ, we have this angle equals to 90 degrees, this angle equals to 90 degrees, this angle equals to alpha, therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this great triangle BSQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that the right triangle AZQ is similar to this right triangle QBS. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. Likewise, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So we should found out that all the figures of this right triangle SQB are corresponding equal to all the figures of this right triangle AQZ, and therefore those two right triangles are similar to each other according to angle similarity rule. Repeat again, we should found out that the right triangle QBS is similar, this is the sign of similar to the right triangle AQZ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side SQ of this right triangle SQB or side AQ of this right triangle AQZ is equal to side QB of this right triangle SQB or side QZ of this right triangle AQZ. Okay, again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side SQ of the right triangle QBS or side AQ of the right triangle AQZ equals to side QB of the right triangle QBS or side QZ of the right triangle AQZ. SQ is 25, AQ is X, QB is A, and QZ is 12. So today we should find out that 25 over X equals to A over 12. Here of course multiply this equation and we found out that 25 times 12 equals to 8 times X. 25 times 12 is 300, so 300 equals to 8 times X. Here we divided this equation by A and finally found out that X equals to 300 over A. So actually found out by solving the quadratic equation, found out that a a can be equal to either 20 or 15. Now, in order to find out what is the real value for a is qb equals to a and b also equals to a. In order to find out which is the real value for a, either it is 15 or 20, I draw this right triangle ABC in the page with this circle that is described by triangle ABC, and analyze this and the new drawing in order to verify what is the correct value of A. So this is right triangle ABC, this is according to the original drawing. Inside this right triangle ABC we have this circle. So, according to what we already found out, QB equals to A, and we know that AQ equals to X, and in the next step we defined the center of this circle. This point is point O. Point M is the point of tendency with this circle. We define the radius of this circle as R. We join points O and M together by straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle that is equals to R. The radius of M that is equals to R, the radius of M is 1 to point M, that is the point of tendency of the BC with this circle. And whenever your radius is 1 to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, point Q is the point of tendency of tangent AB with this circle. So we join points O and Q together by straight line. OQ is the radius of the circle that is equals to 1, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in quadrilateral OQBM, we have 1, 2, 3 angles, and therefore this fourth angle must be equal to 90 degrees inside, and therefore quadrilateral QOMB is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle QOMB, side OM must be equal to the opposite side QB. But OM is out, therefore the opposite side QB must be also equal to R and it's in itself. So in total we should find out that QB equals to A equals to R. In the next step we did the construction, that is to say we extended the radius MO of this circle by straight line until it touches the circle. We define the touching point of the extended radius MO with this circle. This point is point T. When you extend the straight line by straight line, the result MT must be also a straight line. So MT is a straight line. If you focus on the right side of the straight line MT at point O, either sum of the angles must be equal to 180 degrees according to all three. So which angles we have in the right side of MT at point O? We have this angle that is a right angle plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in its size. So we have in the next step we did another construction, that is to say we do from AB we do perpendicular to the from point from AB we do tangent to the circle at point T. Yeah. From AB we do a tangent to the circle at point T. Okay. We define the touching point of the tangent with side AB. This point is point S. So ST is a tangent to the circle at point T according to our construction. The radius OT that equals to R, the radius OT is drawn to point T, that is the point of tendency of tangent ST with this circle. And whenever your radius is drawn to the point of tendency, then tangent ST will be perpendicular to the radius TO. If ST is perpendicular to TO, it means that this angle equals to 90 degrees according to rule 1. So in total, in quadrilateral STOM, we have 1, 2, 3 rectangles, and therefore this fourth missing angle must be equal to 90 degrees in its size. Therefore, quadrilateral STOM is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in the upper rectangle STOM, side TO must be equal to the opposite side SQ. But TO is R, therefore the opposite side SQ must be also equal to R and it's in its length. So we already found out that QB equals to A and A equals to R. Again, A equals to QB equals to R. I call it this here. A equals to QB and equals to R. What about AQ? AQ equals to X, and AQ equals to AS plus SQ. So again, AQ equals to AS plus SQ. So AQ equals to AS plus SQ. SQ is also in total AQ equals to AS plus R. AQ equals to AS plus R, and AQ also equals to X. And AQ equals to AS plus R, and AQ equals to X. AS plus R is definitely greater than R because AS is a positive number. So we can write, say that AS plus R is greater than R. Okay, and from this law inequality, we derive that S is greater than A. Okay, X is greater than A. X is greater than A. Again, X is greater than A. We have two solutions that are possible for A. A equals to either 20 or A equals to 15. We already found out that X equals to 300 over A. Again, we already found out that X equals to 300 over A. If A equals to 15, it means that X equals to 300 over 15, that is 20. So if A equals to 15, then X equals to 20. So X equals to 20. 20 is definitely greater than 15. It equals to A. From this inequality, we will derive that X is greater than A. X is greater than A. So if X equals to 20, then A equals to 15, and it is exactly according to what we already found out that X is greater than A. What about the other solution for A? A equals to 20. So if A equals to 20, from this equation we derive that X equals to 300 over 20, that is 15. So X equals to 15 when A equals to 20. X equals to 15. 15 is definitely less than 20, that equals to A. From this inequality, we will derive that X is less than A. It contradicts our findings that X must be equal to greater than A. Due to this contradiction, we cancel this solution, and we left only with the other solution that is possible for A, that A equals to 15, and when A equals to 15, then X equals to 20 units in its length. So in total, we should find out that AB equals to X is equals to 20 units in its length. Okay, again, the solution to our question is that line segment AP that equals to X is equal to 20 units in its length. Okay, thank you very much.